Hello, everyone. Fantastic to be here, and even better to see such an awesome audience. Thank you for coming to my talk. My name's Patrycja, and today we are going to explore Prometheus corner cases and some traps. So let's get ready for a ride. First, a brief introduction. I've been doing professional software development or IT work for over 25 years. So yes, I do feel like a dinosaur sometimes, especially among you young engineers. Basically, hello, fellow dinosaurs. But it helped me to touch different areas. So I've been doing software, platform engineering, SRE, DevOps, security. Basically, you name it, I've done it. Last couple of years, I've spent as an SRE in a fintech startup. So basically, payment observability was my daily job. So today I'm gonna share with you what I've learned and some corner cases, pitfalls, and gotchas of Prometheus development. I hope that I don't need to ask this question, why do we need observability? Imagine that we could respond like, to a question, is your system working, production system working? Like, is it broken? Since when? Why? And shamefully, I must admit, I've been there too. My only explanation is that it was a long time ago, over 20 years ago, and I've learned observability the hard way. So basically, we didn't have any observability. Our customers were calling us when something was not working in our system. So then we implemented some basic tooling. There was no Prometheus at the time. Fortunately, we have it now. And now it is pretty major project. This is like a CNCF graduated project. Underneath, we have a time series database, and on top of it, we have PromQL as a query language. Some key concepts you most likely are familiar with, like metrics for types of metrics. With metrics, we have associated labels, key value pairs. We obviously scrape metrics at regular intervals. Then those samples are stored as time series in the underlying database. And we use PromQL to access those data. Prometheus together with Grafana and Alert Manager, it forms an pretty popular observability stack. Obviously, we monitor our components like infrastructure, containers, Kubernetes, applications. We monitor to track their health, performance, SLOs and SLAs of our systems. Basically, whether or not it's working well and within our performance requirements. And then we have obviously dashboarding and visualization in Grafana, and alerting and possibly incident response in Alert Manager. I must say that my first experience with Prometheus was pretty good. I was just copy-pasting my dashboards, using some defaults, and the problems arose when I had to investigate like some SLA breaches. It turned out that I ran into some like corner cases, how quantiles are computed, how increase works, and that kind of stuff. So basically, if you use Prometheus for your payment reporting, that's not a tool for the job. But I guess that you know it, or at least you feel it. On some occasions, I ended like that, really, really frustrated, to put it mildly. Anyone here sharing this experience? Raise your hands. Oh, that's like very heartwarming for myself. I'm not alone. It turns out that Prometheus, even though flexible and powerful, is not as simple as expected, and it has some hidden complexity. So let's try to navigate this complexity maze together. So I prepared a series of puzzles, some short problems that showcase some gotchas. And I'll try to ask you for some solutions, or at least what's your feeling and how it works. So basically, this is like my demo Go application, which creates like 2 histograms. We have A duration seconds and B duration seconds histogram. The buckets are configured as you see them, and there is like 98 observations, the first constant observations for each metric. The first one is like recording 500 millisecond duration every 5 seconds. The second one, 900 millisecond duration, also every 5 seconds. So basically, you can see how it looks like on the graph. And now the question. We want to calculate histogram quantile, 0.99 quantile for each of the metrics. And the question, what will this histogram quantile function return as 0.99 quantile value for each metric? I have a couple of answers. So first of all, the actual correct values based on raw data is 500 milliseconds for A duration metric and 900 milliseconds for B duration metric. And then perhaps Prometheus returns the same for both of them, like around 994, or perhaps it returns like the upper bound of the bucket. So this is like 1 second, or perhaps no data are returned as there is not enough sample available to compute 0.99 quantile, or perhaps error is returned as queries are not correct. So I guess that you know that the obvious answer is not correct, but perhaps you want to see the poll, and perhaps you want to answer. It's not. Okay, it works. Perhaps not best, but okay. If you try to answer, I would be very happy to see your guesses. So I suppose that, I'm really curious what's your view on this. And we've got our first responses. So, it's pretty even distribution. Yeah, that's Prometheus. Yeah, I see that you had quite an experience with Prometheus. Error as the queries are incorrect. Okay. Yeah, that's pretty interesting. Thank you for such interesting responses, and I can tell you that it only highlights that Prometheus is not simple. Let's move back to my slides and let's see the correct answer. That's 994 for both. Why? Exactly. So congrats to you, because those two histograms are exactly the same. We need to keep in mind that histograms do not contain actual values. Those are only counts in buckets. So a histogram quantile function is not able to calculate the actual raw value. It can only estimate. So it looks for the right bucket where the desired quantile falls in, and then performs linear interpolation using uniform distribution between the two surrounding buckets. How does it work? So here you can see that both histograms have exactly the same data. All observations fall into 1.0 and plus inf buckets. Why? Because Prometheus buckets are cumulative buckets. So the higher bucket contains all the observation from the lower buckets. And then when you think about linear interpolation with uniform distribution, it's just like all those counts falling into a given range, they cause this range to be divided into equal splits, and then based on that, we estimate the quantile. So here you see like kind of approximation of the actual algorithm. The implementation details may vary a little bit, but the actual idea is as you see that. So basically, that's why we see this 994 for both of them. Then we have a second puzzle. The second puzzle is very similar. So basically, again, we use a histogram with those 6 buckets, 100 observations, and this time also constant observation, but the actual duration is 1,500 milliseconds, so it falls into the highest plus inf bucket. And again, we want to calculate histogram quantile for 0.99 and this metric. And again, let's try to guess what Prometheus is gonna do in such a case. So we have again a couple of answers. So you've already known that this histogram quantile does sort of an approximation based on the surrounding buckets. But here we don't have this higher bucket. We are at the highest bucket. So what does Prometheus do in such a case? So perhaps it approximates between 1 second and like maxint, some sort of maxint. Perhaps it approximates based on 1 second and max float. Let's keep in mind that all Prometheus numbers are floats. Perhaps it just returns 1 second, or perhaps it returns not a number because it's not able to calculate it, to approximate it in any way. So again, let's give it a try And please use your Slido app or open web page. You should see a next poll. Again, quite a split, but here we have a clear winner so far. So let's wait a couple of seconds more. And okay, and I was so hoping that you are gonna get it right, but not this time yet. Yeah, you are changing your minds. Thank you. Okay, 1.0 is correct. Why? Again, you see that all observations fall into this plus inf bucket, and this is a special case. When you read Prometheus docs, you see that if a quantile is located in the highest bucket, then the upper bound of the second highest bucket is returned. So this means like 1 second. What does it mean for our observability? We need to keep in mind that our histogram quantiles are only approximations, that we are not able to assess how much we breach, for example, SLAs in some cases, because we can't have like very high buckets. We need to stop somewhere. Why? Because it's all about cost. If we have a lot of buckets, it means that we have a high cardinality metric. And it means like this is like pretty CPU intensive, it is memory intensive, or if you use like a cloud-based solution, then it means that you pay a lot of money. But if you need to design your buckets to cover your distribution. So if you know that most of your durations fall into like specific ranges, like introduce more buckets to provide better accuracy. Less buckets if you have like sparse data, and obviously you need to be mindful of the costs, whether it is like in CPU or memory or with actual money when it comes to cloud solutions. It is super important when it comes to SLOs and SLAs as well. This is my personal experience. If you formulate your SLOs and SLAs in terms of histogram quantiles, it means that you report actual values to, for example, your customers. And customers or other teams like product, customer success team in your company, they don't understand the details. They believe those numbers. And those numbers are only estimates. So for example, we had a case when a customer was chasing us because the trend was like negative. We were showing that our performance was like declining, even though still within SLA, the customer was concerned whether or not this is like a good trend. So it's better to formulate your SLAs and SLOs around percentages instead of percentile values. And report in such a way that you don't expose those estimates to customers or other teams because they are misleading. And RTFM, all those information is in the docs. So we had a problem with interpolation. Now it's time for extrapolation, which is done in in Prometheus as well. So we have another puzzle. This time we have a single counter, a count. This counter is increased every minute, and scraping interval is 15 seconds. And we want to see what's returned by increase A count for the interval 90 seconds. So basically in 90 seconds, you obviously have only one increase, right? And so the question is, what will increase A count for 90-second return? Is it 1.0 sharp? Is it 1.0 plus minus some small epsilon? Because if you know increase is only like a syntactic sugar over rate, so it uses rate underneath. Perhaps something like, or anything between like some range, 0, 3, or perhaps it depends. That's the best answer in IT always, right? So it could be, it depends, none or this 1 plus minus epsilon. What's your guess here? Waiting for your answers. Yep, this epsilon was convincing, I see. Yeah, it's always about this precision, like floating point precision is fun. I love this puzzle when you add 10 times 0.1 and you don't get 1. And yeah, you really believe it's all about epsilon. We have a clear winner now. And unfortunately, again, I'm sorry to say you're wrong. So that's anything from 0 inclusive and 3 exclusive, kind of. So why does it happen? It's like a delicate situation between like a slowly increasing counter, because you take a look that our scraping interval is 15 seconds, while we increase our counter only once per minute. So we have 4 samples, which are exactly the same for each value, more or less. So it's kind of a stairs. And that's how it looks like for the graph, rendered by Grafana for those increases. Obviously, this is not like fully trustworthy because Grafana does some adjustments as well. But you can imagine that. And I can only tell you that for each interval, it looks a little bit different. And you get like different data, different spikes or more smooth line. It depends. But basically those values shuffle between 0 as the lowest and like 2 point something. Why? Here you have a piece of Prometheus code. This is like extrapolated rate function. This is like a utility function used by all 3 major functions, rate, increase, and delta, I rate as well. So basically, it extrapolates the first and last sample. So it is difficult to get the boundaries of the interval exactly aligned to your scraping interval. So those samples like differ. And if they are those start and end values are not exactly aligned, then we have some sort of extrapolation. And it causes such strange side effects. Here there is a really interesting issue opened in Prometheus repo. Unfortunately, after a very long discussion, it was closed and resolved, and it was stated that this is like desired or designed behavior of Prometheus. So basically, it means that you can't trust your Prometheus data. It is good to see the trends, but you need to understand what's going on underneath. And you need to understand all the assumptions and ways of working. The basic approach is also to align scrape interval and eval interval. And Grafana kind of does it automatically now for a couple of years already, because if you use rate interval variable in Grafana, basically it is set as 4 times scrape interval, just to avoid some issues when zooming in into like very high resolution. However, this doesn't solve the issue I showed you with increase. With rate interval, this increase spikes as well. So another lessons learned here, we shouldn't alert on absolute rates. We should alert on anomalies. And basically, that's something I've seen as well. I've seen a lot of alerting or assertions because, for example, we did chaos testing and we had some assertion on whether or not our traffic is flowing at a given range. We shouldn't do that because it was like pretty flaky and dependent on actual traffic rates and those Prometheus extrapolations or approximations in general, because rate does extrapolation and interpolation as well. I do have a couple of more puzzles, so perhaps this one is pretty simple because error count matrix is increased only once, and the question to you, if we have such an alert increase on error count over 5 minutes greater than 0, does this alert fire or not? Let me grab your answers very, very quickly. Please try it out. Yeah. I think that this one you will get right. Yeah, it won't fire, but we... Are you doing that on purpose? Please, let us cast a single pole right. No, it won't fire. Thank you so much. You know it, and you guessed it right. It won't fire. Why? Because it was the first observation, no samples before, so there is nothing to increase, because for increase you need at least 2 samples. And if you don't have your metric initialized, so this initial 0 is not visible anywhere. So that's another problem. And here, initializing metrics to 0 may be a problem with dynamic labels. We need to be very careful, again, with sparse metrics like slow counters with gaps. And also we need to rethink our alerting. What I found useful is like changing your approach and changing your mind. Instead of finding problems, focus on what it means to have a happy path. With happy events, you have like more events coming, more observation coming, and you don't have such problems with those error metrics, which are usually sparse. So SLOs in this case are like a conceptual difference and to show some different solution than only focusing on technical details. One more puzzle, perhaps we won't go through the poll now, just to showcase some Another corner case is when we have a service full down. It means that this service does not produce any metrics, so no metrics scraped, and we have alert on some full service up equals 0. So basically, here, will this alert fire? No, since there is no metrics. So it can't compare it to 0 because there is like no information. So this is again a pretty common situation when we don't think what will happen when we don't have this metric available. We rely on metrics, and our regular approaches use metrics. And in many cases, we need to use like this absent function and combine absent with like a specific condition if necessary. We can use or and concatenate those two clauses, or we can use a separate alert per clause. And this is also very important in case of SLOs, because in some cases we didn't get alerting on our SLOs because we didn't have any metric. So later on, we introduced this alert on no metric. Okay, so just to sum up, high cardinality I mentioned already with CPU and memory intensive. Metrics silently dropped in case of cloud solutions pretty often, and high cost. And I can only say that's only the tip of the Prometheus iceberg. So be aware that a fool with a tool is only a fool. Let's not be fools, and let's educate ourselves on Prometheus corner cases just to keep fighting with it, right? So it's all about continuous learning, and that's what conferences are for. Thank you for coming. Thank you for such an engagement. And if you have any questions, just approach me during a break and we can chat. Prometheus and Kubernetes are my go-to topics.